Okay, so let's discuss the finite difference method. And as I was saying in the beginning of the class, when we were talking about mathematical strengths, this is all based on Taylor expansions. This is the basic concept of this whole very powerful method, Taylor expansions. In fact, the finite difference method is the oldest numerical methods for partial differential equations, and it's believed to have been introduced by Euler. So we're talking about 1780 something. I mean, a long time ago. So the first step is what we want to do is approximate derivatives in some sort of numerical way. The first step is to define what's called a grid, okay, on the domain where the fluid exists, okay? This, in finite difference, usually means a locally structured set of lines, which are two families of lines, like in this picture, they're vertical and horizontal, but they don't have to be vertical and horizontal. They just need to be two families of lines that intersect in one and only one point. So it needs to be that specific in the sense that two lines of the same family, we call them grid lines. Two grid lines belonging to the same family must not intersect. And two grid lines belonging to different families need to intersect only once, only in one point. That's what we call structured. This is called a structured grid. So what we have is, for example, is if it's a case like this, horizontal, vertical, and they all intersect at right angles, we have that each little node, each point in this grid is identified by two indices, I and J, indicating the particular grid line of each family that intersects there. This unique set, so each node has a unique, in this case it's two-dimensional. If it was three-dimensional, we'll have an additional, line going perpendicular to the paper, and we'd have I, J, K, but it would be the same idea. So each node uniquely defined by these two indices that identify the grid lines that intersect at this point. Then the neighbor points of IJ are going to be defined implicitly by, say, -1, +1. Then you can say exactly who's on either side. J plus 1, J minus 1. That identifies the neighbors. So we can know which are the neighboring points. So what we're going to have to solve a differential equation on the grid is that there's going to be an unknown value of all of our field quantities like velocity and pressure per grid node. So each grid node holds a value of the unknowns. For example, U, V, W, P, and so on. Velocity, pressure, particularly. And also each grid node will provide one algebraic equation So obviously we want to have the same number of unknowns and equations, so we can solve this. And this algebraic equation will consist of a relation between the variable values at that node and some of the neighbors. Okay? Let's call it field values, the unknown values of velocity and pressure. At the node and some of its neighbors. So this is the first step. We construct sort of this geometrical object that we can put on the domain of the flow, and we're going to use that to represent all our unknown variables at each point of this grid. And at each point of this grid, we're going to write an equation, an algebraic equation. And then we're going to have equal number of equations and unknowns, and we're just going to solve this with a linear solver, of which you know Gaussian elimination, but I've told you there are many more. Okay? So let's see how that works. So, first, recall the definition of a derivative. This is an example in one dimension. The definition of a derivative is, for example, the u dx at xi is the limit, when delta x tends to 0, of the function u at xi plus delta x minus the function u at xi divided by delta x. You must recall, of course, from your basic calculus. So, a geometric interpretation of this is that the first derivative, the u dx, at a point is the slope of the tangent, right, to the curve ux. So suppose we have here in this cartoon that I've made a plot of u of x. Okay, that's the darker line, u of x, with respect to x. And so if this point here in the middle is the point xi, then the slope of the tangent represents the u dx. Well, we could use, we're talking about 1D, we could use just the letter d instead of partial, but let's just keep it general because we're going to generalize this to more dimensions. So the slope can be approximated by a line which passes through, say, two neighbors. So that's the first thing that we can do. And so let's consider that this point here next to it is xi. So this is going to be xi plus 1. And this point here is going to be xi minus 1. This is the same as the grid that we had before, but in one dimension. Only one dimension. Okay? So we're going to approximate the slope where the slope represents the derivative by a line passing through two nearby points. So we have one option is what we call the backward difference, and this is if we consider the point itself and the previous one to approximate the slope. So it uses xi and xi minus 1, or xi minus delta x, if delta x is this distance. And this one also. For the time being, we consider delta x to be uniform and representing the difference between 2 points, any 2 points. And we would construct a grid, in this case one dimension, grid of points, in all the axis x, and delta x is the difference between all of those points. We call the backward difference the approximation of the slope using xi and xi minus delta x. We call the forward difference the approximation of the slope which uses xi and xi plus delta x. And the final one that we can think of, just using the neighbor points, would be something that uses both xi minus 1 and xi plus 1. There are 2 points, and that's called the central difference. The final one is the central difference, and it uses the 2 points on either side of xi. So this cartoon illustrates, perhaps you can see that some approximations may be better than others. You can see if I look back at what the exact is. Okay, look at the cartoon here, and that's the slope, the exact slope. In my cartoon, the backward difference is that one using the point and the one before. Forward difference is that one using the middle point and the one next to it, plus delta x, and then there's central difference. And it does seem like central difference approximates a little better, doesn't it? And also you can imagine that if delta x is made smaller and smaller, the approximation is going to be better and better. Can you imagine that from the picture? Yeah? And those are 2 crucial points, that some approximations are better than others. And that the quality of the approximation will improve as you make delta x smaller. Or we say, as the grid is refined. Yes, Tim, you have a question there? No? Okay. Okay, so how do we write those approximations? I've shown you pictorially how one can imagine these approximations, but let's see how one would write down the equations for these two. So that's the exact slope right there that we just had, and the backward difference is the first one. So let's do a backward difference. For the backward difference, let's assume for simplicity that delta x is fixed, so it's going to be equal to xi minus xi minus 1, and for all I, so it's a uniform for this whole grid, one-dimensional grid that we've imagined to be dividing the whole x set of spatial variables, independent variables, and u of x is our dependent variable that we want to find numerically. The backward difference approximates the slope, the u dx, by using u of at xi minus, so let's call it just I. So let's write let's say u at xi, we're going to use the notation, it's just ui, so that to make it shorter. So this is going to be ui minus ui minus 1. This point is I, and this is I minus 1. and divided by delta x. That's the approximation that we make of the slope. That's the backward difference. Now, if we want to make the forward difference, then we would approximate the u dx by ui plus 1 minus ui over delta x. And if we want to use the central difference, we would have both ui plus 1 and ui minus 1. But notice that the difference between these 2 points now is 2 delta x. You agree? You agree with that? Yeah, okay, good. So those are our finite difference approximations. That's it. So the next question that we want to ask is, what is the accuracy of such an approximation? What is the error that one makes if I write this algebraic representation for this differential operator? Okay? So the accuracy of finite difference approximations is the next question. So now we consider a Taylor expansion. Taylor expansion, we're working in just one dimension, and so it should be okay. Consider Taylor expansion of u of x in the vicinity of point xi. So u of x is equal to u of xi. It's now the full definition of Taylor expansions, plus x minus xi times the first derivative, du dx, evaluated at point I, plus x minus xi squared divided by, times, oh yeah, it is 2 factorial, isn't it? 2 factorial du, second derivative, du dx at, again, point I, plus we have a third order term, x minus xi cube over 3 factorial third derivative of u with respect to x at point I, and so on and so forth, right? Infinity, to infinity. So that's our Taylor expansion. So what we're going to do is now we can replace in this formula ux by either one of the 2 points on either side. So basically, rather, I'm going to write it more short by just putting x. And we replace x by xi minus 1 or xi plus 1 to get expressions for the variable values at these points with respect to the neighbors. So let's look at first if we do xi plus 1. We're going to get expressions for the variable at xi depending on the neighbors, right? So we just use this equation for the Taylor expansion over and over again. So for example, if I consider xi plus 1, and I'm going to rearrange by, what we want to do is find an expression for the derivative, right? And here is my derivative, right? So what I'm going to do is take this to the other side, basically take this to the other side, divide by delta x, and take all of the other, just isolate this guy, because this is what we want to approximate. So I'm going to write du dx at point I is equal to, consider now I'm using xi plus 1. So we have u at I plus 1 minus ui divided by x minus xi from here, minus all of these terms. But these terms are also divided by x minus xi. Remember, we divided over the whole equation by x minus xi. So minus x minus x, oh sorry, it's x I plus 1. This is I plus 1. It's a little bit messy. Let me write it again. And this one is the same, xi plus 1 minus xi. This term had a square, but I've divided over one of those, so one of them goes away. We still have the 2 factorial though. And I have the second derivative, du dx, second derivative at I. Minus the other term, xi plus 1 minus xi. It was a cube, but I've divided over by 1, so I'm only left with square, 3 factorial, and the third derivative. And there are other terms that we don't write. We call them higher order terms. So now you can see that if delta x is small, okay, if delta x is small, then all of these terms here can be neglected. The only possible problem would be if we have very high derivatives, but then let's not worry about that. Let's consider that the derivatives are well behaved, so we can neglect all that. So by neglecting all these terms, you see that the largest term that was neglected is of order delta x. We say this is of order delta x, and this is the largest term neglected, which means that the error that we make by neglecting all of these is we write big O to represent the order. The error is order delta x. Does that make sense? When I'm going to make the approximation that the derivative is only this first term here, remember we did this from the Taylor expansion, and I'm going to neglect all of those other terms, and I conclude that when I use my finite difference approximation that I have inside the red box, I am making an error which is of order x. You see that? Now we can see that as delta x tends to 0, the error tends to 0. Which means that the approximation converges. The approximation of the derivative that we just made converges to the exact value of the derivative. This is called the truncation error. This error here is called the truncation error. because it represents, all the terms that we neglected. Okay, similarly, we could do with the same thing for the backward difference and for the forward difference, right? So I'm going to write those again. I'm going to write this expression that we have right here again. And I'm also going to write it, but for the backward difference, which would have I minus 1 instead of I plus 1. Okay? Are you ready? Can I erase this? Yeah, okay. Well, that's the one that we just had. So we have forward difference is the one that we just did. I'm just going to rewrite it. We are approximating du dx at point I by ui plus 1 minus ui divided by, I'm just going to write it delta x now. You know that it's delta x is the difference between x at I plus 1 and x at I. And the other term is delta x over 2 factorial, second derivative from the Taylor expansions and solving for the udx, second derivative I minus delta x squared divided by 3 factorial, third order derivative and other terms, higher order terms. For the backward difference, I'm writing it short there, FD, BD for backward difference. We approximate the same derivative du dx at the same point I, but using the other neighbor. So it's going to be ui minus 1 over delta x, and the errors are the same. Actually, no, they're not the same because we're going to have a sign that appears from the delta x there when I do, depending on whether it's even or odd power, I'm going to have plus or minus here. So the odds, this is going to be plus when it was minus, but I moved it to the other side, over 2. So I'm sorry, I'm perhaps skipping a few steps, but I hope that you can see that if I have xi, so let's write it up here. If I have xi minus, no, sorry, xi minus 1 minus xi, then this is equal to minus delta x. So in the first equation that I had for Taylor expansions, I said we're going to replace x by xi plus 1 or xi minus 1. When I replace it by xi minus 1, I'm going to get this minus sign on all of the terms that have delta x. So this is why the formula turns out to be a little bit different with alternating signs, plus, minus, plus, minus. No, it's a minus. Okay? And so now we note that the, yes?
Should there be a factorial by 2?
Yeah, but 2 factorial is equal to 2, so I'm, yeah, so it's 2 times 1. Correctly written, it does belong there, yes. Now we notice that the first order terms here have opposite signs. So the dominant first order error term or truncation terms have opposite signs. So I'm going to add the 2 formulas. To get I add here, and I'm going to have a 2, but I'm going to divide the equation by 2, so I'm going to write it on the other side. And I have, when I add these terms, this one cancels with that one, right? So I have ui plus 1 minus ui minus 1. And I have delta x here, but I need to divide by the 2 when I added these. Okay, so I'm going to write in my head, we have 2 delta x. Are you able to follow those shortcuts? Yes? You see that? I added these 2, there's a 2, I divide it over. Then I add these and they cancel out completely. These are the same. When I add these 2 equations, they cancel out completely. And these, they have the same sign, so I have minus delta x squared divided by 3 factorial, did I also divide by 2? And third order derivative. Yes? Oh, you add them, there's a 2 and it cancels out. Thank you very much. Yes. 3 factorial. I'm sorry, that was me saying something and writing something different, but you are correct. 3 factorial, which is 6, right? And we have other terms which I will ignore. And we can see now, this is squared, that what we obtain here is the central difference formula. This is the central difference formula. And this is what we're going to neglect in the formula. And you can see that this is the truncation error, which is now of order delta x squared, which means that if x is small, this error is much smaller than the error made with the finite difference, with a forward difference or backward difference. These two, forward difference and backward difference, have an error of order delta x. The central difference has an error of order delta x squared. The approximation is better. As delta x is made smaller, this one the error goes to 0 quicker. So this is very important. What this means is that, for example, if you have, for example, let's consider a very small case, a one-dimensional domain between 0 and 1 with delta x suppose equal to 0.1. So we have just 11 mesh points here, right, in the small line. If the error is order delta x, we are saying that it's going to be approximately in the order of 10% error. It's quite big. Well, this is kind of a crude example. But if we go to the second order central difference, we call it second order because it has second order error. Central difference will have an error of order delta x squared, which would be of order 1%. So you can see with the same amount, with the same number of points, you can get a much more accurate result. This is the difference between low order and high order methods. It's a crucial point in numerical methods. Yes?
So that neglected term, is that encountered, like, is that included in the differential?
Yes, we're neglecting the whole thing, and with the idea that if delta x is very small, this is going to be close to 0. If the function is smooth, well-behaved, nice, then these derivatives are never big.
So in order to calculate your error, you just calculate delta x.
you don't actually calculate, you say it's of the order of, because it's delta x squared multiplied by a number. Whatever this number is, okay, it's always going to be the order delta x squared. So if I take delta x and I divide it by half, the error will go by the 1/4, will reduce by 1/4. Multiply with whatever number is here. If this number is 26 or 85, it doesn't matter. When I reduce delta x by 1/2, the error gets reduced by 1/4 because it's proportional to x squared. You see that? So it's, as you make delta x smaller and smaller and smaller, the error will get smaller and smaller and smaller. It converges. So remember, here we have the Navier-Stokes equation. So what we're going to do to start our discussion of computational fluid dynamics is work with some simplified model equations. So this is the Navier-Stokes equations right there that you know and have come to love, and represent the flow of fluids of an incompressible Newtonian fluid, which is many of the fluid situations we deal with as engineers. So from the mathematical point of view, in the Navier-Stokes equations, we see that the terms that represent viscous effects, this is the viscous term, or diffusive effects, viscous or diffusive effects, are associated with the second order derivative in space. We see as well that the convective terms, remember what is our convective acceleration, this term right here, let me call this 1, let me call this 2, and that makes it easier for me to say 1 here, 2 here. Convective terms are associated or appear in the equation as first order derivatives in space. So what we do is try to look at the simplest possible model, mathematical model, that will represent both the convective or diffusive terms, and look at them separately too, because numerical approaches, computational approaches, sometimes are better suited to represent one or the other, and a particular numerical approach will be developed for each one, okay? And so we are going to look at the simplified model equations which represent one or the other effect. So, and the reason is we have to develop models that we have to develop numerical approaches, computational approaches that are appropriate to these terms, second order or first order. And so in the process, for example, of discretization, a scheme, an approach to discretization that works well for diffusion might not work so well for convection. And so we look for the right approach for each one of these terms. And the way that we look at that is by looking at simplified equations that have only one of these components in them. Do you remember when we were looking at the Navier-Stokes equations, and we were looking at some simplified models in the beginning, and we looked at some very, for example, we had Poiseuille flow, and that was dominated by viscosity. You know, we had the boundary layer case, and there was some unsteady term there, and we looked at each of these simplified models, and we said we can see here in this simplified situation there is a balance between, for example, unsteadiness and viscous effect, and all the other terms disappeared. We do the same thing now, but with the purpose of understanding how these numerical approximations that we call finite difference behave in each case. And so, because the numerical discretization needs to be appropriate to the physics, and so, for example, a numerical discretization that is appropriate for diffusion terms, which are the second order derivative terms, might not work well for the convection term. And so, for that reason, we will look at simplified model equations that contain just one of these effects one by one, so that we can understand the properties of the discretization for convection, and separately the properties of convection, of discretization for diffusion, and then we know that in the Navier-Stokes equation we're going to have all of these things together. So in fact, the first one, so what you're going to do, what I've done there's a course that is offered for graduate students and also for seniors, or if they want to take it, in computational fluid dynamics, and what we've developed for that course is a set of steps that can incrementally go to the point that you can have a Navier-Stokes solver in 12 steps. What you're going to have to do for your next assignment is the first 4 steps. And I'm going to just quickly show you what these 4 steps might look like. The first one is going to be just linear convection in one dimension. For linear convection in one dimension, just give me 2 minutes. I know you're eager to go. For linear convection in one dimension, you want to discretize the UDX. You see the UDX appears? No, forget about that. The UDX appears here, and we're going to use one of the finite difference approximations for the UDX. You need to approximate the UDT, and then put the approximations for the UDX and the UDT back in the equation. Okay? And this is what's going to be explained on Monday. This is one case, 1D linear convection, and you obtain a discrete equation. So let me just quickly show you what it would look like. So for example, you would just do, for the UDX, you write UI minus 1 over delta t, delta x. For the UDT, you write, we're going to use a different index. Instead of I, I'm going to use n. UN plus 1 at the top minus UN, and both at point I, divided by delta t. And then I put these two back in the equation, and I have a numerical representation of that equation. So we're going to do that for 1D linear convection, then you're going to do it for 1D. So it's linear because, see, this is a fixed velocity there. Then you're going to do it for the case of nonlinear, where instead of C you have U. Then you're going to do it 1D diffusion. And finally you will do 1D convection diffusion. That's going to be the assignment, and next class is going to be explained step by step.